Welcome to this Math Media Club video on complex numbers. My name is Archie, and today I'm going to be going through the basics of complex numbers and some worked examples you could find in IB exam situations. So this video assumes some basic knowledge in number and algebra. You should be able to just follow along. If you can't, or if I mention a different topic that you haven't reviewed yet, I'd suggest you go review it and then come back to this video. So I'm sure a lot of you have heard what complex numbers are. Specifically, say you have the square root of 4, okay? Let me zoom out here. Square root of 4. Now, this is going to be equal to 2. But when you look at square root of -4, what happens then? If you take a look at the graph, okay, and you graph y equals x squared, you have this a line like this, right? And this is a very bad drawing, but if you look closely, you'll see that this graph never goes into the negative domain. So if, let's say, x equals square root of -4, then x squared must be equal to -4. But x squared is never equal to -4. So what we have done as mathematicians is created this unit, this imaginary unit called I. This I is equal to square root of -1. Now, with the properties of the square root, we can say this is not, there are some exceptions to this property, but we generally say that this is equal to square root of -1 times square root of 4. And this is hence equal to square root of 4 is equal to 2i. And this opens up a whole new world for numbers. I mean, now every number in the world, every number that exists has a square root. So negative numbers have square roots. Square root of -9 would be equal to 3i. Square root of -3 would be equal to root 3i, and so on. So basically, this minus here is not an obstacle for us anymore because of this imaginary unit we have defined as I. Now, this right here would just be called an imaginary number. Okay? This is an imaginary number. However, say we have something like 2 plus 3i. So it's 2 in the real domain and 3 in the complex domain. Or I'm going to introduce that now. The complex domain means that you have a combination of a real number and an imaginary number. And technically we just say that, but these coefficients could be 0. So all real numbers are equal to complex numbers, or R is a subset of C. Okay. Now, 0 technically is a real and complex number. So basically, R is a subset of C. But so basically this means that all real numbers are complex, but all complex numbers are not real. So typically we like to define it with the letter Z, like this, to A plus, such that there exists some complex number Z in the complex domain, which is equal to some real part A plus some real part times the imaginary part I. So this states that A is a real number, so is B. An example of a complex number is going to be equal to 3 plus 2i. This right here has a real part 3 and an imaginary part 2i. And this is going to make more sense when I introduce this here. So we actually have something called the complex plane. And in the future, when you get more deep into it, you'll be asked to draw Argand diagrams, etc. So the complex plane is like a normal XY plane or XY axis that you see, okay? And we call this part the imaginary part and this part the real part, okay? So complex numbers are defined as points on this axis, on these axes right here. So for example, the number 1, well, it's just real, and it's just um, it's 1 unit to the 1 unit on the real axis, right? So the number 1 would go right here. Similarly, on the imaginary axis, these are just coefficients of I. So the number I would go right here. Or number 4I would go right here. And when you add these parts together, the real and imaginary parts, you get these complex numbers. So say the number we had used as an example here, 3 plus 2I. Well, it'd be 3 in the real direction and 2 in the imaginary direction. So it'd be right here, 3 plus 2I. And this tool is actually rather powerful. I mean, for like this, complex numbers are used in electrical engineering, physics, um, and they just open up they are a fundamental part of algebra. And now this is the basics of complex numbers. This is one way to represent them. However, if you look at this, from the origin point 0, 0, there's actually a vector defined like this, such that it goes from the origin to some complex number, some arbitrary complex number here, and it forms a vector, something that has magnitude and direction. So it has some angle right here, theta, and some magnitude, r. Now, if you think about this, right, if you think about this triangle right here, uh, you have, well, this distance r, you have the imaginary part a, and you have the real part b, or the real part a and the imaginary part b. And since it's a vector, we can actually define this length right here as the magnitude of this vector, which is done using bar notation. This is also a right angle triangle, and we have the same angle theta right here. Now, based on some basic trigonometry, we know that tan of theta is going to be equal to the opposite over the adjacent, which is equal to b over a. And therefore, theta is equal to the arctangent of b over a. Now, for this magnitude thing, we can just use the Pythagorean theorem. So we know that the hypotenuse is going to be equal to, well, uh, the hypotenuse squared is equal to the sum of the sides squared. So in this case, the magnitude of z squared is going to be equal to a squared plus b squared. So the magnitude of c is going to be equal to the root of a squared plus b squared. And this actually allows us to express complex numbers in this form. So first of all, say you have some angle theta, right? You know the angle theta you're given. And you know on a unit circle, let's say this distance is 1. This distance right here, or the real part a is going to be equal to, well, okay, wait. So cosine theta is going to be equal to a divided by 1, where a is equal to cosine theta. Okay? Now, say this changes from 1 to some value r. Well, then we know that a is going to be equal to, if we move this r to this side, a is going to be equal to r cosine theta. Now, say we have the same thing here, we'll call this b. B is going to be equal to r sine theta by the same case. And so we get b is equal to r sine theta. Hence, this number right here we get is going to be the sum of these two components, right? So a plus bi. So we'll call z is equal to a plus bi, which is equal to r cosine theta plus r times I times sine theta, which is equal to r cosine theta plus I sine theta. Now, this is actually an intro to polar coordinates, where instead of typically for polar coordinates or vector notation, you'd use the unit vectors I, j, and k, but that's a topic for another time. But this is basically the same thing here. So we're converting polar coordinates with r and theta to these Cartesian coordinates, a and b. So yeah, so we know that a plus bi is another way to represent r cosine theta plus I sine theta. And another identity, which is called Euler's identity, it's quite famous. It's this r e to the I theta is equal to r cosine theta plus I sine theta, or e to the I theta equals cosine theta plus I sine theta. And this is actually what is used to prove the fact that e to the I pi plus 1 equals 0. But we'll get to that another time. This can be proved using the Taylor series for cosine and sine, but that will be proved another time. And with this, you can use this to solve questions. So you may be asked to find the magnitude of, say, the complex number z, if z is equal to 2 plus I. And in this case, you know a equals 2, b equals 1. So the magnitude is going to be equal to the root of 2 squared plus 1 squared, or root 4 plus 1, which is equal to root 5. Or you may be asked to convert these standard form complex numbers to polar coordinate, to the polar form. So you have here the magnitude is root 5, and theta, as we said earlier, is going to be equal to the arctangent of b over a. And in this case, b is 1, so it's going to be arctangent of the half. And typically you want to do these operations in radians. So arctan of a half is around 0.464. So basically this states that 2 plus I is equal to e to the I, or sorry, root 5 e to the I, or sorry, 0.464 I, because a plus bi is equal to r e to the I theta. That's the basics of complex numbers. There will be some more videos on some worked examples soon, but I hope you're able to learn this. If there's some concepts you don't understand, feel free to look it up, review some other examples, and yep, thank you.